Hey, recording is rolling. Welcome to Thursday, October 26th. I got some demos signed up for you guys. We're going to finish that 12-row table that we've been working on last couple days. This one right here. Then escape speed, I've talked about before, but I want to explain for you guys where that comes from, the derivation. Tell you guys something about power, and then a lab for tomorrow. Gonna set up a lab for you guys for tomorrow that involves pendulums. Right. Before I switch over these demos, here's some ways to quantify energy. I mentioned this the other day, but let's tack some numbers to it. Lots of ways to measure energy. In this class, we have joules. 1 joule is one. Where's poster for this one? Right. Got a new poster for this too. So 1 joule breaks down to these units here. That's most of what we care about. Right? But there's other ways too. 1 kilowatt hour. If you guys ever get an electricity bill one day, probably be charged for kilowatt hours. That's like power times time, right? That's equivalent to 3.6 million joules. 1 calorie, that's the energy it takes to raise the 1 gram of water by 1 degree Celsius. That's like 4.18 joules. Right? Now, food calories are actually kilocalories. So if you talk about nutritional calories, you're actually talking about thousands of those. So 1 food calorie, with a capital C, is 1 kilocalorie. That's 4,000 and something joules. Right? If you ever see a British thermal unit, that's a little over 1 kilojoule. All right, let's switch over to these demos. Demo time. Switch my screen over here. All right, let's go. There we go. Dominoes. All right, let's do Paul Hewitt. Paul Hewitt. All right, one more of these. All right, so this one I won't 100% explain today, but at least be able to plant this idea. So got this bowling ball here, and we'll come back and revisit this idea in the future. So I got this bowling ball top of this track. Oh, I wonder where this is going. Release that, and oh, it's got there in the loop. Oh, right around the loop, wearing a helmet. Oh, but six made around, so he's all right. But let's do a rewind. Because what if I can pause this right? I did. All right. What if right about there the ball runs out of juice and like falls off the track and bonks him in the head? Right. So you guys know from a couple weeks back that there is a minimum speed to make sure that it doesn't happen. It's something to do with like square root GR, where R is the radius of that circle there, right? But now let's take that the next step and say, well, how far, like how high up did you have to release the bowling ball in the first place? Guys, everybody look here. Okay. How high up did you have to release the bowling ball in the first place so that it can reach that speed, so that it can make it around, then fall off the track at that point? Like for example, if you dash off a horizontal line from that point, go straight over, and release the bowling ball from that exact same height, would that be high enough? You're right, it would not be, because if you released it from that exact same height, see, it would speed up on the way down, then would slow down on the way up, and then when it gets to there, it would run out of steam and bonk the guy in the head. Right? So it has to be higher than that point, but how much higher? There is a theoretical answer to that question, like a minimum height. So, like I said, for now, I'm just going to plant that question. We're going to revisit that probably next week, I think, something, because tomorrow we're going to do a lab. So, all right. So, yeah. So hold on to the idea, or maybe you can even solve it yourself, maybe. All right. So let's go ahead and finish this table. All right. Got to about here yesterday. Last one we looked at was the spring fires the ball vertically into the air. We're looking at a ball, spring, or system. All the energy was in the spring, 1/2 kx squared. It went to some maximum height. Now at the maximum height, it's all in GH, right? And the speed at that point was 0. But maybe some more interesting questions for that would have been something. Why did we not include kinetic energy? There's no kinetic energy at point A. There's no kinetic energy at point B. There was in the middle, but we don't care about all the middle stuff. All we care about is what's going on at point A, what's going on at point B, right? So a more interesting question, what's the final speed, could be, if you know any 4 of these variables, can you solve for the 5th one? Like if you know the spring constant and how much you squash it and the mass of the ball and the gravity field, can you solve for how high it's going to go? Or if you know how high it goes, could you solve for like what's the spring constant? How stiff is the spring? Right? Or how about a proportion question? Guys, here's a good proportion question. What if you run this, you smash the spring some value, boing, goes up some height, right? Then you go back and rerun that experiment, except you smash the spring twice as much as before. So you double that x. How high will the ball go compared to before? Because if you double that x, guys, what's a factor of 2 squared? Is that 4 times? Is that going to be 4 times the height it's going to translate to for the same mass ball? Okay. All right, now, next one. We got a block falling from some height onto the spring. Is going to maximally compress it. Well, that looks like a really similar set. That's kind of the reverse of what we just did, right? So I think we still got a ball, spring, earth system. So it's the same type system. Okay. So maybe you should just reverse these two, because it looks like it's starting from some height. Here, I meant to flash this in front of the camera. You guys know we're just taking this from our like equation bank, right? So just any of these expressions, and really just focus on the yellow ones. So far in this table, we've only ever used some combination of these 4, if you even keep it track. Right? It's just these 4 expressions over and over and over for this entire table so far. Right? And so I think it's going to be this kind of energy turns into that kind of energy, pretty much, right? So mgh from point A turns into 1/2 kx squared at point B, right? And we can equate those two because the energy is conserved, and then you can solve for stuff. So if you know any of those things, you can solve for anything else, right? So if the spring is maximally compressed, what's the answer to this question? What's the speed of point B? Yeah, also 0 meters per second. Yeah, probably not the most opportune question for that setup, but that would be the answer to that question. Right? Another detail about this one. I remember seeing this question when I went to college. This question was asked, except there was a slightly more complicated version. You had to consider that as the spring was being smashed, the ball was still being pulled down by gravity. So this x is part of this height fall, right? So if you ever see this question in the future, this is kind of a simplified version of this, right? But suppose you go to college and you see this exact question pop up, right? And they assign it certain values to say you drop it from 1 meter, or like 100 centimeters it takes to reach the top of the spring, and then goes ahead and smashes the spring an additional like 5 centimeters. They say, well, that's actually like 105 centimeters that it fell. That's all part of that h. The drop height to the top of the spring plus the additional x, right? We're gonna call that h plus x of sand, right? So right? Just look for something like that. All right, all right, you guys ready for those last two? So we've done 10 of these examples so far. Again, the 10 that we've done have all been some combination of just these 4 yellow boxes, right? Now these last two are going to be challenge questions type, right? Challenge questions, right? You guys stretch your imagination a little bit. We're going to involve these 2 green rows, which don't show up as much, right? I'm going to start with this rolling kinetic, this rotational kinetic, right? So let's compare rotational kinetic to just plain linear kinetic. You guys remember linear kinetic energy motion is like 1/2 mv squared, right? Well, in a rotational sense, 1/2 I omega squared. That looks like a really similar structure to that expression. Instead of the mass of the object, now it's rotational inertia. Instead of linear speed, like meters per second, now it's angular speed, like radians per second. Now, the turntable, you guys remember those turntables? Okay, so you guys probably have a pretty good idea of what radians per second angular speed is, because we did quite a bit of work with that, right? Now, what I mentioned just once before, very briefly, was this I values, rotational inertia. We're going to get more into depth in that in December. So we're going to solve this now a little bit, and then yeah, we'll do more in depth later. Right? The one time I mentioned this I value, rotational inertia, I think I brought out these 2 meter sticks. Basically, these 2 meter sticks have weights attached to them. They're the same weights, except one of these has the weights taped near the middle, and one of them has the 2 weights taped near the ends. Here's one end, and then on the other end of that weight, right? Okay. Now, if I pick both of these up, I'm going to pull these off screen. So if you're watching this video at home, then just off screen, right? So I pick this up. If I close my eyes, they feel like the same mass and the same weight, right? But if I grab these at the middle and I start rotating them back and forth, so kind of in front of the camera, right? If I got these both grabbed at the middle, I start rotating these back and forth. Now they feel different, right? And you guys can see it, see in front of you. Right? You guys see how the one where I grab, where the weights are near the middle, has almost no rotational inertia. It's really easy to change the state of motion. But the one where the weights are at the end, right? It's really hard to change the state of motion. It's really hard to shake it back and forth, right? Because it has so much more rotational inertia. So it's not just how much mass anymore. It's now where's that mass located. Here, pass these around. You guys want to get your hands on this really quick. Again, this is more of a December type topic, this rotational inertia, but that's what that I represents. Okay? Now, if you have a ball that's rolling down an incline, it matters how that mass is distributed. I bet if you had a race for different types of balls, like if you have a basketball where all the mass is pretty much on the outside shell, versus maybe a baseball where it's pretty closely evenly distributed, versus maybe one of these solid cylinders, right? Those all have different mass distributions. They all have different I values, different rotational inertia. And they would, somebody's going to win that race to the bottom, probably the baseball, I'm thinking. And I think the basketball is going to lose that race. And they would have different speeds at the bottom. Right? Another detail, notice it says rolls without sliding, right? Which means that you do need static friction. If there was no friction, it wouldn't even roll at all, right? So you do need static friction. But interestingly, the static friction does not actually remove energy from the system. Like the last time we saw a friction was the car breaking to a stop. And that we had to treat as an open system, and it was taking energy out of the system. That's not going to be the case here. Here, friction is not acting as a non-conservative force. Okay? So the energy will stay in the system. We can treat this as a closed system. I'm going to have the ball in the system. I'm going to have the, because we're focused on the ball, I'm going to have the earth in the system because it's changing height. It's being pulled down by its weight. I'll also include the incline because there is a frictional force on the incline. But again, that friction force is not taking energy out of that system. So this can be a closed system. That's okay. Right? At point A, I think it's all MGH, right? All MGH. That's the supply of energy. Now, by the time you get to the end, point B, the different ways to solve this, we're doing in energy context. So, of course, I'm going to do the energy context here, right? We think of it sort of having like 2 types of energy. There's translational kinetic energy, your 1/2 mv squared. Like if you point a radar gun at that ball at the bottom, it has some linear speed. But don't forget that it's also rotating. So I'm going to say plus, and here's your 1/2 I omega squared, right? So this type of energy at the top of the hill, MGH, turns into a combination of linear plus rotational kinetic energy at the bottom. Okay? Right? Again, depending on what type of rolling object you have, do you have a baseball, a basketball, or like a solid cylinder? Right? They'll be rolling differently at the bottom because they have different I values. Right. Right. So just for today, I'm not going to do any more algebra on this one, but I do want to tell you guys how this would finish off. So just kind of back that big picture. How would you finish this? So you can equate these. If it's 1,000 joules here, maybe it's 1,000 joules here. That's good. Okay? This V and this omega are related, and I gave that to you guys in this hint here. But you might remember that from before. You guys remember V is equal to omega over R, or if you like, or sorry, I'm so sorry. V is omega times R. Omega is V divided by R. Okay, so you can substitute that omega out with V divided by R, right? Then that V would be same thing as that V, and then R would be the radial size of the ball. Right? I is a function of this M. It's some function of mr squared, but it depends what shape it is. It's a basketball, it's a baseball, is a cylinder, right? But you could get this I in terms of this M, and then also factor that out, right? And then it would eventually cancel out because this M on the left, right? So it just depends how the mass is distributed, right? So we're gonna leave that right there just for today, but maybe in December might come back and solve something more like this. Okay, so just plant this idea for now. Okay. And the last one is also a challenge question. It involves two asteroids that are gravitationally attracting. Now, if you see two things gravitationally attracting, getting closer to each other and speeding up, maybe your first thought is, oh, that looks like it's going from potential energy to kinetic energy. And if that was your thought, then you're right, right? But the way we've been doing this so far, like if you have a ball falling towards the Earth, I might say, like Galileo drops a ball off the tower, say this potential turns into this kinetic, and then solve that and call it a day. Right? The speed at the bottom is square root 2gh. Right? Okay. But that relies on this g being constant, this lowercase g, this gravity field. Okay? That's not going to be true for two asteroids that are pulling closer to each other. That g is going to be getting stronger, stronger, stronger. Right? So we're going to have to not use mgh. We're going to have to use the more universal form of potential energy, which is a funny looking form. It's negative gmm on r. Right? So why does it look like that? Why is it negative? Right? I'm going to take guys 3 different stories with this green line right here, right? 3 different stories. One story is, well, we're going to use that to answer this question on this table. The second story is I want to convince you guys why you can use this to solve for escape speed, which is something you saw a week or 2 back, but now I want to drive it for you guys. And the third story is I want to show you guys why this green line actually simplifies to this yellow line MGH, as long as the radial size is relatively small. You have a small height change compared to the size of the planet. This can actually simplify to this, right? So one at a time. First, let's answer this question. These 2 asteroids out in space gravitationally attracting. Let's say it's at point A, they start from rest. So what's in the system is each asteroid, say each asteroid. Right? And if they start from rest, there's no kinetic energy, but there is a potential energy. Right? And that potential energy is negative g m on r. I said each asteroid has the same mass, so it's the same mass there. If you want to call it m squared, you could do that. Right. That kind of looks like a gravitational attraction. You guys remember force due to gravity was gmm over r squared, right? But I also remember energy or work is like force times distance. Well, if the distance is the radial size, okay, that's why that gravity force times r, one of the r's would cancel, right? Now, why is it negative? Hold on to the idea. I'll explain it with the second story. So, but for now, let's just treat that as negative. Okay? And this would be the radius a, right? Be r sub a, because later on they're going to get closer together, right? So by the time you get to point B, let's say there's still some separation distance. Like I still got negative gmm on r, but now it's rb, right? Plus now each asteroid is picking up some speed. So I'm going to say plus 1/2 mv squared for one asteroid, plus another 1/2 mv squared for the other asteroid, right? See that? So now the energy went to 3 places. Let me make up some crazy numbers just to give you guys a big picture perspective. Suppose you start off with like 1,000 joules of potential energy. I know it says negative. I'm really simplifying, right? It's like 1,000 joules of potential energy. And now as they gravitate closer together, maybe like 500 joules goes here, and the other 250 and 250 go here. So 500 plus 250 plus 250 adds up to the original 1,000, right? Or how about the fact that I did make this negative? Let's look at that, right? So you guys see RB is less than RA because they're getting closer. Right? What happens in a fraction when you divide by smaller numbers? What happens to the overall fraction? It gets what? It's bigger. When you divide by smaller numbers, it gets bigger. Combine that with the fact that this is a negative value. So maybe I should have gone with a negative example. Maybe this is like a negative 1,000 joules to start out with, right? Right. And then this might turn into, I should have done that. So kind of scratch my last example. That was a dumb example. Okay. But let's do these new numbers. Let's say it starts off with like negative 1,000 joules, right? And then it goes to like negative 2,000 joules. So the fact that it got larger, but it's negative, actually makes it a smaller number, doesn't it? Right? A larger negative number, kind of like if you're $1,000 in debt, and later on you're now $2,000 in debt. Oh, great! Now you're poorer, right? So negative 1,000 joules goes to negative 2,000 joules, and now there's 1,000 joules left over for kinetic energy, maybe 500 joules here and 500 joules here, right? Okay, right. We could go ahead and solve for the speed at that point, but also this one I'm just gonna kind of leave there. I just want you guys to see the big picture of how that works out. But you could just equate this and then solve stuff, right? But I want to give you guys two other stories for this universal form of potential energy, right? What? Oh, and guys, this table, we're done with this table. Just turn this into the grade trade before you leave class today. I'll check it off and give you guys points for that, as long as you have all the rows that we've done, as long as you have everything that I've written. If you were absent one of the days, then you can turn it in tomorrow would be all right, because you guys know I have all these on camera on Google Classroom. Okay, so we go. That's kind of going to the grade tray. All right, so here's escape speed. Now I did show this to you a week or two back. I said when we get to energy, I'll explain it. So, well, now's the day. So here's the story that's going to attach to this. Suppose we have a big empty universe, right? There's nothing in the universe except for two objects. I have a planet on one side of the universe, and on the here, guys, everybody look up here. Everybody look up here. Right, on the complete opposite side of the universe, I have a small rock. You guys got that? I have a planet over here and a small rock over here. Let's say they're separated by like several light years, so just crazy far away from each other in an otherwise empty universe. Now, do you guys think there's a tiny, tiny, tiny gravity tug between these two? Right? They're going to pull towards each other. Newton's third law, equal and opposite forces. Except the giant planet probably barely moves because it has so much inertia. I bet the small rock is going to like fall across the entire universe. It's eventually going to, bam, crash into it. You guys think it might take like, oh, I don't know, maybe like a couple billion years or something, right? So they start from rest, just floating around, and this rock falls from the edge of space and bam, crashes into the planet. How fast does it crash? I mean, it fell from the edge of space. Is it infinitely fast? It's not infinitely fast. There's a finite number. It has to do with what the masses are for each of these objects, right? Especially the planet. Actually, it really depends on the mass of the planet, right? How fast it, bam, crashes into it. So here's how you solve it. And this is what leads to this poster in the setup. I see 3 lines here, right? So I'm going to start by saying when these two were floating at opposite edges of the universe away from each other, I'm going to consider that to be a zero energy situation. So I'm going to say zero energy in the system. There's obviously zero kinetic because neither of them are moving. They start from rest. But I'm also going to consider it to be zero potential energy, right? Now, here's where you have to use your imagination a little bit. You might say, well, hold a minute. I see a huge, huge, huge height, sort of, right? Shouldn't that be huge potential energy? But I'm going to consider that to be zero potential energy. What that means then is that as this falls towards the planet, right? The rock falls towards the planet, right? I'm losing potential energy. Oh, that's why potential energy from a universal point of view is always going to be negative, because it starts out zero, and then you only lose from there. Okay, so potential energy from this point of view is always negative. Okay. Now, if you start off with 0 joules of energy, that loss of potential energy is picked up by kinetic, but it still has to zero out because of conservation of energy, right? I only had 0 joules to start with. I only ever have 0 joules. Whatever I'm losing in potential, I'm picking up in kinetic, right? So just 1 FMV squared. Okay. And then if you solve for this V would represent the crash speed, pow, at the surface of the planet, as long as this R corresponds to the radius of the planet at that point, right? This R starts off as infinity. Maybe that's another way to think why this would turn to 0 infinitely far away, right? Guys, what happens when you divide by infinity? See, what is 1 over infinity? 0. That's a good one to know, right? Guys, for example, if you buy a lottery ticket, you have a 1 in 20 million chance of winning. You basically have a 0 chance of winning, right? But maybe that's another reason to think this would be start off 0. Okay? Anyway, later on, like at point B, this can be the radius of the planet. You solve for this V, you get the crash speed. So here's the crash speed. It's square root 2gm on r, where m is the mass of the planet, r is the radius of the planet. Okay. So there's some finite crash speed for falling from the edge of space. But if you think about it, you could turn that around and say, well, how fast do I have to throw this rock straight up into the sky so that it could go all the way to the edge of space, right? And if I threw it like a smidge faster, it would just like fly away forever, right? That is an escape speed concept. And it turns out to be the same value, just the opposite direction. So there you go. that is also, that expression therefore also represents escape speed. That's where that comes from. Okay, so kind of a abstract story you have to connect to that, but like 3 lines, right? Go, go, go. Okay. One last thing here, guys. Everybody look up here. Okay. One last thing I want to tell you guys with this green line. I want to show you guys that this green line does in fact simplify to MGH as long as you are at the surface of a planet. Okay. Let me find my notes from earlier. Right, you guys are taking notes, right? You guys are taking notes. Where's my notes on this? What? Okay, well, I don't know. I'll just make up something from scratch here. Right. I'm sure it's like not too far. I'm just not seeing it. Right. So let's go to a planet like Earth. Right. So I got a planet like Earth. Right? And Earth has some radial size. Call that R. Right. Except let me actually call that R1. Maybe that goes to like sea level. Maybe have a mountain, like Mount Everest. And I go to the top of that mountain, and I'll call that radial size R2. Right. Now, if that represents Mount Everest on Earth, this is definitely not to scale at all. Do you guys know if Earth was the size of a bowling ball, it would actually be smoother than a bowling ball? Like an actual bowling ball probably has like little tiny scratches and stuff you just like ignore, right? If you blew up a bowling ball with scratches to the size of Earth, those little scratches would be like deeper than the Mariana Trench and like taller than Mount Everest, right? So, so the Earth is like really, really smooth. And talking about like, if you drop something off Mount Everest and like fell into the ocean, to us, like at the surface of Earth, we say, ooh, that's a huge height change, right? Like that's a huge, or call it H, right? Height change, right? But in terms of the radial size of the Earth, that height change is like hardly anything at all, right? So really small proportionally, right? Right. So this H is R2 minus R1. Hold on to that idea. That's gonna come back later. Okay. Let's say, what's the difference in potential energy between the top of Mount Everest and sea level? Right. So the difference in potential energy, I'll call it delta U. Right. Difference in potential energy is negative G M M on R2 minus negative G M M on R1, where capital M is the mass of the planet, and lowercase m, maybe that represents like the mass of the object that's being dropped, right? Going from the top of Mount Everest down to sea level, right? Guys get that? Okay. Now, maybe I want to get a common denominator. Could I get a common denominator? What do I have to multiply the first fraction by to get a common denominator? R1 over R1. And the second guy I have to multiply by R2 over R2, right? Fractions, right? So let's do that. So the difference in potential energy from the top of the mountain down to sea level is, right, got a negative GMMR1 minus a negative. Oh, guys, minus a negative. Does that just turn into plus? GMMR2. This is all over R1 times R2. Is that like that? Right? Ooh, can I factor some stuff out of here? Like, I see a universal gravity constant. I see the mass of the planet. I see the mass of whatever's being dropped. Can I just factor all that out? Right. So the change in potential energy is, right, I'm going to take a universal gravity constant, the mass of the planet, mass of whatever is being dropped. Also pull R1, R2 out, R1, R2, right? And then whatever's left on the inside is just negative R1 plus R2. And I could reverse those and do R2 minus R1. Right? Isn't that what that would be? Right, second story. Right. Now we're getting pretty close to the outcome, right? Because remember, I made this whole comparison like Earth compared to a bowling ball, like how crazy smooth it is, right? Like Mount Everest would hardly register the size of a bowling ball, right? R1 and R2 are almost the same thing, right? Like R1 is approximately R2, which I'm just going to call collectively R, right? Yeah, this goes hand in hand with the gravity field not really changing that much from the top of the mountain down to sea level, right? So this R1, R2, I'm just going to call R squared. And when I do that, ooh, what is this right here? GM over R squared, playing off the mass of the planet. What does that represent? GM over R squared. What does that represent? The gravity field. Like, guys, if you plug in those values for Earth, universal gravity constant, mass of Earth, radius of Earth squared down here, what number do you get? 9.8 meters per second squared. This right here is lowercase g. Okay, here's the mass of whatever is being dropped, just lowercase m. Right? And oh, what is r2 minus r1? The height of fall. And look what we have, mgh. So the change in potential energy is mgh. Right? Simplifies mg. There you go. Right. So that was, remember what I promised you guys when I was filling out this paper. I said this green line simplifies to this yellow line as long as the height change is small compared to the radial size of the planet. And there it is. There's the first. Okay. Okay. You guys good there? Okay. All right. All right. So a couple more things. I'm going to come back to this pendulum. Let's look at power, because a few days ago in your notes, I told you guys these two new units. I said energy in joules breaks down to this, right? And we've been doing a bunch of stuff on that energy table, conservation of energy, right? I did briefly mention this, so let's look a little bit more at power, and we'll solve a couple of problems with this, right? Power in watts, right? You guys ever look on a light bulb? It says like 40 watts on it, right? That is a rate that is pulling energy off the grid or out of a battery in the case of a flashlight. Right? 40 watts is like 40 joules per second. That's what that represents. Breaks down to like these units. Right? So let's solve a couple of problems that involve power, and I'll give you guys an interesting formula that you can alternatively use for power too. Right? Let's have a story of pulling an elevator. Here we go. You guys are writing this in your notes, right? Let's lift an elevator. Up an elevator shaft. Right, so let's get an elevator shaft going. I'm gonna have an elevator down here. Say the elevator has some mass. I'll even give a number. Let's tag some numbers to this one. I know we've been solving a lot in terms of variables the last couple of days. Call it 1,000 kilograms. Okay, and let's have this elevator be lifted some height. Okay? Maybe there's a elevator cable, and there's like near the roof, like a motor, it's like pulling the elevator up. Okay. Let's have a height change of 50 meters. How about that? 50 meters. 50 meters height is going to be pulled up. It's an Earth's gravity field. You guys know Earth's gravity field. Let's just round it to an even 10 meters per second squared, like we usually do. Let's start with that. All right. Now let's go back and review like work and energy. Right? So first question is like, how much energy does it take to lift? Right? Like, because you can imagine this motor up here is probably connected to the electric grid, and we're going to have to pay the utility company for the electricity to lift the elevator, right? It's going to cost some money. We need to pay for that electricity, right? So, how much energy are we talking about? Can I just do work equals force times distance? Can I just do that? Force times distance, right? And if we pull up this elevator at constant speed, then what that means is, in terms of free body diagram, the tension in the elevator cable, which is the force that I'm using to lift it, would be equivalent to the weight. So that's what I'm going to do here. I'm going to substitute for this tension force. I'm going to say it's equivalent to the weight of the elevator. That's true for pulling up at constant speed. Oh, and the distance I pull it up, isn't that just the height that it's pulled up? So this is like h. Oh, and look at that. Actually, we kind of talked about this before. The work is equal to the potential energy that you give it, mgh. Isn't that a version of that? Right, you guys remember that from before? All right, so let's put some numbers in. The mass of the elevator I called 1,000 kilograms. The gravity field I called 10 meters per second squared, and we're lifting this thing 50 meters. So bam, bam, bam. It's 500,000. That's 500,000. Guys, what's the unit? That's 500,000. What? Joules, because it's work, energy, measured in joules, right? Or could you call that 500 what? Kilojoules, 500 kilojoules. You could do that, right? Okay. Now let's take this to the next step, because I want to say something about power, right? Right here. Let's bring this poster here. Power measured in watts. I wonder how many watts is this motor, right? Like what rate is it pulling energy? Okay? But to know that, you have to know something that I have not told you yet. What information is missing to be able to answer that question? How many watts? What did I not give you that you need to know? Here's a hint. Look at the units. Guys, 1 watt is 1 joule per second. How many seconds? Yeah, time in seconds. Exactly. Yeah. So I need to throw in one more detail. Let's say this all happens in a time interval of 20 seconds. Because if it takes like 10 minutes, but probably really small power to lift it all day, right? If it happens in like 1 second, especially you type it, hey, let's go to the 50 meters in 1 second, right? There's probably a lot of power. Right? So let's just call it 20 seconds, just make a number, right? I wonder what the power output is for this whole process happening in 20 seconds. So power, I know, is work per time, right? Or energy per time, work per time. So it's a rate that this is happening. So I've got 500 kilojoules in 20 seconds. Is that, here it is, 25 kilowatts. 25 kilowatts. You guys see 25 kilowatts of power? 25,000 watts. So this motor at the top is pulling 25,000 watts, right? Right. Great. Good so far? Right. Because we're going to do one more power example. I want to take this to a different perspective. Because let's look at that expression. Power is work per time. That's how I've been defining this, right? Work per time or energy per time, like a rate of work. But you guys know that work is force times distance. So could I write that like that? That'd be the same thing, right? Right. But instead of roping together the force and the distance to make work, which is what we just did, what if I do a different perspective? What if I wrote these two variables together? Guys, what is distance over time in physics? What's that called? Speed. Hey, could that be power is equal to force times speed? Right? I should work too, right? Let's run the numbers. Let's see if this works. So the force to lift it, let's do the exact same scenario we just did. The force to lift it is like 10,000 newtons, right? 1,000 kilograms, 10 meters per second squared. That's 10,000 newtons. So I got 10, I'll call it kilonewtons. How about that? 10,000 newtons. Is that 10 kilonewtons of force at, see, distance over time for velocity? Well, I've got 50 meters. It happened in 20 seconds, right? 50 meters in 20 seconds. So that's the speed, 50 meters in 20 seconds. So I got 10,000 newtons, 10 kilonewtons at 2.5 meters per second. Put it all together, is that 25 kilowatt? Hey, 25 kilowatts. That's the exact same thing we got before. I mean, it had to have been. It's the same scenario with the same numbers, but it's from a different perspective. The first way we did it, we said, well, power is a rate of work, rate of energy. That's like work per time. We got that. Okay. The new way we did it, we said, well, could you like force times velocity? Oh, we got the same thing, right? So that's a pretty cool one to know. I should probably make this one a poster. Power is force times speed. I'm surprised I haven't made a poster on this one yet. So, all right, should probably do that. All right, I got next on my list. All right, last thing, pendulum lab. Tomorrow, I'm gonna have you guys do a pendulum lab. So probably have time to have you guys set up the table in class today. So let me show you guys what I want you guys to do. If you're in class, yeah, you guys see a ring stand and a string and a mass on it. So you guys see that pendulum class, right? Right. And if you're watching this video at home, well, here's a picture of that. Right, so ring stand, string, mass on the end, right? I wonder how fast it's going at the bottom, which would be the maximum speed when it is like speeding up on the way down and past that point, it like slows down on the way up. So, right? The energy version of this, like from that perspective, hey, this is kind of like Paul Hewitt's bowling ball. Remember, he didn't smash his teeth, right? I wonder about, oh, conservation of energy. Hey, here's conservation of energy. Okay? And we can pick 2 points, just like we did for that entire energy table, and equate the energy because we could call this a closed system. You know, like the mass Earth system could be like a closed system, couldn't it? Right? Right. And it would be all potential energy here, and it would be all kinetic energy down here. Well, I'm saying all potential energy here. That's true if it starts from rest. Right, so MGH at the top turns into 1/2 mv squared at the bottom. Right. If here, guys, really here. If you give this a push, then you have to also add 1/2 mv squared here. Now I put this in light gray because usually that's equal to 0. But if it was there, then this is how it would play out. It would end up as like v naught squared underneath the square root. Right? You need to add it. Right? So just to look for that, right? Right. But if you ignore that, it's just potential to kinetic energy. Right. So there's one last tricky part to be able to figure this out, which you have to figure out what is this height change as a function of the length of the pendulum and the starting angle from the vertical. Maybe it's like, oh, I don't know, 70 centimeters long, and you pull it's like 30 degrees, right? I wonder what the height change is going to be. Okay? So let's do some geometry. You guys ready for some geometry? Okay. So here's the length of the pendulum. Right. Here, ooh, do you guys see a nice right triangle? You guys see a right triangle? Is this distance right here L cosine theta? Right? L cosine theta, right? Right? Right. Now, this length is constant, so this length is equal to this length, which means that this height change is the difference between the full length and L cosine theta. Right? You guys see that? Isn't this height change equal to the full L minus L cosine theta? Which is what I wrote right here, L minus L cosine theta. Now, if you want to, you could factor out this L. That's not 100% necessary, but you could. And that would look like this. Right? L times 1 minus cosine theta. Right? Ah, that's what that is right there. Right? Ooh, do you guys remember Galileo dropping balls off the Leaning Tower? And how fast was the crash speed? It was square root 2gh. D equals square root 2gh. D equals square root 2g. And then instead of h for a height change, I have that whole expression right there. L1 minus cosine theta. Right? Look at there. Look at there. Right? So tomorrow, you guys' lab, I want you guys to use these speed gates. You guys think you could put a speed gate right here and the pendulum swings through it and can tell you exactly how fast it's going, like give you an empirical reading, right? And do you guys think you could also do this calculation and then compare the two and see how close it is? Because it should be the same thing, right? You're gonna find out. So if you guys got some paper, then go ahead and make this table. I'll make it with you guys. If you don't have any paper, here's a stack of paper right here. Okay? So let's all make this table. We're gonna all make this table. And this is going to be your lab table tomorrow. Right. So let's call this, okay, so there's the setup there. Right. Here's the title, here's the table. Let's put it all together. We're going to call this pendulum speed lab. You guys write your name on your paper? You guys write your name? Right. So it's your name, your title, pendulum speed lab. Let's make a table. This would probably be a really minimal table that you want to have. Just put a bunch of columns on this. Okay, maybe that's too many columns. I don't know. Right. Well, different trials going on. Right, 1, 2, 3, 4, 5, whatever. Right. Then different variables and units. Okay. Ooh, guys, notice what I did not include on my table. I didn't say anything about the mass of the bob, did I? Notice I didn't say that. Right. Now, why? Because at least in the energy setup, the mass should cancel out. So there was mass, but then it canceled out, right? If you want to, if you're really scientifically meticulous, maybe you have a column for mass. Maybe you want to include that. What's the mass in, I don't know, kilograms or grams? Right? It could be an extra column, right? But you definitely need to know these other things. What's the length in meters? Or you could do centimeters, maybe. Right? It's up to you. Figure that out. What's the starting angle from the vertical? They would call it initial angle, right? Maybe in degrees. Right. Right. And then I need 2 different columns for speed. I need to know what is the speed empirically. So I'll say empirical, which is a measured value, maybe like meters per second. Right. That's what the speed gate's for. Right. You see, you get an actual empirical measurement. Right. And then what is the speed? I'll say calculated, like as a theoretical value. And that, okay, well, it have the same units, right? But that would be equal to this expression right here, square root 2gl 1 minus cosine theta. So the right here equals square root 2gl 1 minus cosine theta. That poster is also hanging up in my classroom. Make sure the square root bar extends over that entire inside expression right there. Yeah, just like that. Right. So there you go. Right. Now, this isn't going to be a crazy fancy lab tomorrow. There's not really going to be an independent variable or anything crazy like that. What I want you guys to do is just maybe try different values. Or you could, I don't know, try different lengths, different starting angle theta. Just go crazy. So it's not going to be like as structured as some of our other labs are, right? But you really want to keep an eye on these last two columns right here. Okay, what is the speed value according to the speed gate versus what did I tell you it should have been according to conservation of energy? And hopefully these two columns all the way down are pretty dang close to each other. But time will tell. All right. All right, we got about a minute left in class. So guys, before you walk out of class today, make sure that you turn in your energy table. And just as long as you've completed all 12 rows, or, well, okay, I know we didn't quite finish the last two, that's okay. These last two boxes can be blank. But as long as you did everything that I did in class, I will check that off and give you guys some points in the grade book. And that's a wrap on today.